So in the previous lecture, we were discussing about sigmoid neurons. So what was the difference in the sigmoid neuron? So we saw that we didn't want a harsh function that we had, usually the activation function that we had, it was taking decision very harshly, that we had the step function in that. So we wanted to replace the step function by the sigmoid function so that we had the smoothness, something of this sort. Okay, so what were the advantages by using this sigmoid? The first thing which I wrote was smooth. It is smooth, that is, it is continuous, it has it does not have any jumps or cuts. And second thing was it is differentiable. And why do we care about differentiability? Because we will be optimizing these functions, will be either taking minimum values or maximum minima, will look for these optimal points. So we have to somehow differentiate the function. So it is very good if we have a function which is differentiable. So these were the things that we have. And now the point is, if we have the sigmoid neuron, okay, now we have to somehow as we saw it in the neuron, we had Mikolopit's neuron, we have perceptron. So we there saw a perceptron learning algorithm. Then we there saw error surfaces. So similarly, I just remind the problem that we are actually doing in machine learning. So the core idea in machine learning is basically you have to learn things. So we have data, so which we have spoken in length in one of the previous lectures. So data is like this: xi, yi. If it is supervised learning, so this xi is a bunch of features. So it can be xi1, xi2, something of this sort, xin. Okay, and correspond to this, there is this label. So these are the features and this is the label. So what we assume is that we assume data contains information and we have to learn from the information. And there is a generating process. There is a generating process. Okay, and this generating process somehow can be captured and we can relate it with the functions. That's what we had seen in the previous lectures also. So let's suppose if something is there, if you see images, if you see faces of people, or if you see, let's suppose, images of cats and dogs, if you see videos, if you see weather, so all of these things, they have an underlying generating process. Okay, and that generating process can be defined somehow by functions, or in terms, if we see it through a probabilistic lens, so we can say that there is a probability, there is an underlying probability distribution. There is an underlying probability distribution. Okay, now what we had is, you have this features like this, you had x and y, you have features and the corresponding labels. So now we know that these features are somehow related with these labels because of that underlying process, because of the underlying distribution that we have. Now let's suppose I can write this x, consider x as all these features, and now they are somehow related with this y, they are somehow related with this label. So we call that a function. Okay, so this is the underlying generating process. So yeah, and you know that with every function, so if it is a non-deterministic process and if it contains the things which we are not certain about, so we use the concept of probability that we discussed in mathematics to deal with such things. Okay, that's why we say that there is an underlying distribution that can explain this process. Okay, so now we will have to see what do we mean by learning. So this is our data, and then we have our model. So what is model now? The first thing we saw is data. So I'll write these one by one. So data, so it is something of this sort. So we have data from 1 to n. I'm writing it in supervised setting. So xi is the feature vector and yi is the corresponding label to it. And then what basically model is? So model tries to approximate this. So now we don't want to come up with this exact function. We want to approximate this. So approximate the underlying function. So this is what we want. So we want to approximate the underlying function that has generated this data. Okay, so how do we do that? So in deep learning, we do that by parameters. So we now will have parameterized function. So how do we see now this in deep learning? So we have to model this. So model will be seen something of this sort, because this will be a composition of a lot of functions. So we'll have initially one function, then composed to some other function. So at the end, we'll have some function which will be parameterized. So we'll get some input and there will be some parameters theta, and this theta will be these weights and biases. Okay, and this is the function by the help of which this will predict function, and this is what we call our model. So once we find these thetas, once we find these weights and biases, so this will be our model. So I can call this as my model. Okay, and now we know about these parameters, and then we should have somehow a learning algorithm. We should have a learning algorithm. So before learning algorithm, what we should know is we should know the objective also. So learning algorithm will work on some objective. So we have done detailed treatment of this, so all the steps in the pipeline. But here I'm just giving you again some revision, and maybe so that you get a reminder of things. So we have data which contains information, and then we want to learn a model of it. So what is meaning of the model? The model basically is the underlying function that we want. So here I want that parameterized function, and the parameters will be this theta. So this theta contains weights by these will be our parameters. So now we'll have to learn these parameters. We'll have to learn these weights and biases. So we'll have some learning algorithms, but these learning algorithms will work on some objective. So we'll have a function. Okay, we have those loss functions which we want to minimize, something of that sort. So we'll have an objective which we want to achieve. Anything that you do in life, it must have an objective. So let's suppose we come in this class. The objective is to grasp the concepts that I'll teach here. Okay, and the objective is to have a healthy discussion so that we increase the knowledge. Okay. Similarly, whenever you do a machine learning, deep learning task, there should be some objective. So in usually in the case is that you have to minimize the loss function. So you define a loss function based on the problem statement, and this loss function is defined based on problem statement. So what a problem you are solving. So you will have a problem statement corresponding to that. You will construct a loss function, and then you will try to minimize the loss function. Okay. So and then we have these learning algorithms. So learning algorithms will try to they'll try to achieve these objectives. So what are learning algorithms? You have gradient descent. So and you have a lot of things, and you have these optimizers defined, and there are a lot of things that that go in this. Okay. And now let's suppose if we take an example, that is the running example. So in our movie case, so we have these xi will be the features. So features of movies like genre, actors, etc. In the items case, we were having two running examples. If we want to see if a customer will buy the product, so there we will have average time spent, and all of these features will be there. And then yi will be the feature 1 or 0. So this will be 1 or 0. In the movie recommendation case, it will be if a person will watch the movie, should we recommend the movie, or in the case of while we were saying that did we have to sell the product, so there we will say that customer 1 means customer will buy the product, and 0 means it will not. And similarly, let's suppose model, if we see, so model here can be, so we can define this model like this. So we have y prediction can be 1 divided by 1 plus something of this sort. So we can use this sigmoid neuron to learn it. So we can use sigmoid neuron to learn it, and then what will be our so now how to learn this. So now question becomes how to learn it. So in order to learn these things, so let's suppose I'll take an example. I'll take a pretty easy example. So initially what we can do is, so let's suppose we take some example in maybe 2D. So we have 2 points. Suppose we have a point here and we have a point here. Now you want to learn this by using the sigmoid function. So what you have is you have your weights and you have your biases. That's what you have to learn. Okay, so how do you capture this? So you apply sigma of W transpose X plus B, and you want to adjust these weights and you want to adjust these biases so as to fit this. Now you know that this is a sigmoid. This is a sigmoid neuron. So somehow we should get something of this sort. Something of this sort, maybe roughly. I'm not able to make it correctly, but I hope you get the point. Okay, something of this sort. So what I want is that these 2 points should somehow lie on this. So they should lie on the sigmoid curve. So when I construct this curve, they should lie on this. And if I let's suppose have these 2 points, if I now have 1 point is here and 1 point is here, now you can see that sigmoid will be somehow like this, something of this sort. Okay, and you will see that sigmoid will shift here and there. Now what I'll do is, so once we have this, so I'll write a code for this so that I'll show you that we have these points, and then what we can do initially is we can do the guess. So we can do guesswork. Okay, hit and try. So we'll attempt to adjust these weights and bias, and then we'll see what is the sigmoid form, and we'll see where is the can we get some optimal value, can we somehow decrease the loss. Okay, and everything will be constructed by loss. So we'll have to come up with a loss function. So in this case, we have also discussed in the previous lectures, we'll use mean square error loss. So mean square error, so how do we compute that? So you'll take sigma of this W transpose X plus bias, and then this will be our predicted value, and then there will be some actual value also. Consider this xi, so W transpose Xi plus bias minus yi, and we'll square it up. Okay, and we are now squaring up, and this will happen for all the values from I is equal to 1 to n, and we'll take an average of this. So this is called mean square error that we have seen. So this is our prediction, and this over here is the actual value, and this is we're taking mean of this. So this is mean square error, so we are taking the square of this. Okay, so this is what we will have, and we have to define sigmoid also. If we have sigmoid of x is 1 divided by 1 plus e to the power minus x. So this is how we will define sigmoid. So now what we can do is we have these weights and biases here. So we have to adjust these weights and biases that you see over here. This is the weight these are the biases. So one algorithm could be, so we could randomly do that. So what is the meaning of random? So we'll put these weights and biases and compute this error. So we want this error to be minimum. Okay, and we want this error to be, and I said that these error functions, if you plot this again is a surface. So we can call these things that we can have an error surface over here. Okay, so we'll have curve, a sigmoid curve of this sort, which we'll get once we give the value w and b, we'll get a curve of this sort. Okay, and initially if you put these values randomly, if you have these w weights and biases randomly, so what will happen? You will get some random curve. So if we keep on doing it randomly, if we keep on randomly doing that, so once we, in a hope that we'll see somehow we'll if we get the least loss, let's suppose we do it for say 1000 iterations. So in 1000 iteration there will be a weights and biases which will give us the least error, which will give us this error will be the least error. So we'll say that okay, this is our optimal. But here you understand that we are doing it by guess. So everything it is done by randomization. There is no algorithm. So I basically want you to take to gradient descent. Why is the need of gradient descent? Okay, let me code that up first. I'll go step by step to do this, and then maybe we'll do it by hand. Before writing the code, we'll do it by hand. Okay, let's suppose we have the points. Say I have defined points over here. So I have three. Let's suppose I have three points. So we have 3 points. Let's suppose the value of these points are 0.5, 1, and the other point is 2.0, 1, 0, and third point is minus 1.0, 1. So you can see that these, let's suppose consider these as features. So this is our feature, and this over here is class label. So this is the label that we have. Now we want to learn these things. We want to learn because this is the data. So this is our data now. As I said that first we'll learn to apply machine learning and deep learning by hand, and then we can use the computers to speed it up. Okay, otherwise you should be able to do machine learning and deep learning by hand. The only advantage computers will provide you, they will crunch these numbers at a large scale. Okay, now you have this data. Now what you have to compute is, you'll have to compute the sigma of, let's consider this z. So what is our z in this case? So in this case z will be w transpose x plus bias. Okay, so I can write it 1 divided by 1 plus e to the power minus z. So this is what we will compute. This is our model. So I encourage everybody to ask questions if you don't understand. So this is our model. Okay, and this is our data. This thing over here is our data. And I will have to come up with a loss function. So loss function, as I earlier said, it will be mean square error. Okay, so how to define that? So summation of I is equal to 1 to 3 because we have 3 data points. So what we'll do is, so we'll apply this sigma, we'll apply this model. Sigma of, so what is the value? W, xi plus b. And then we'll say what is the actual. So this is predicted, this is actual, and we'll square it up. Okay, so we'll square it and we'll take the average to 1 divided by 3. So this is mean square. So this over here is our objective or loss function. Okay, and our job is to get as minimum value as possible. Okay, so this is the thing. So we will initially, what we'll do is we'll randomly set these weights and biases. So these are our parameters. So what here, if you see this w and this b, these two things are our parameters. So we'll randomly set them initially, and then we'll keep on iterating through this, and we'll keep on randomly maybe going through 1000 iterations, and we'll see what is the least mean square error that we get, and we'll plot two things. So one plot will be, we'll plot this sigmoid, basically the curve that we want to fit, and we'll also plot the error surface. So because this thing, if you see, so this is also a function, so this also has a surface associated with it. So according to w and b, so you'll also get the errors corresponding to those. So we'll also plot that. Okay, so this is the thing that we want to do. And initially, let's do it by hand. If we want to do it by hand, say, okay, I have some calculations over here. So let's consider this w to be minus 3.21. Okay, calculations can be wrong, but you can correct them at your home then. So let's suppose bias is equal to 1.83. So this is what we want to do. So what will how will the algorithm start? So now let's suppose these are the random weights and biases. So I'll just show you the one step, and subsequent steps you can do accordingly. So now we'll do this linear combination. We'll compute z1. So we'll see this z1 is equal to wx1. So z1 basically means for 0.1. So for 0.1 has x1 is 0.5 and its corresponding y1 is 1. So this is x1 feature and we have y1. So now we'll compute this. z1 is equal to wx1 plus bias. So if you compute this, wx1, this will be minus 3.21. Okay, and then we know x1 is 0.5, and then plus 1.83 is the bias. So if you compute this, this will come out to be, I think, some 0.225, something of this sort. Calculations can be here and there, but I just want you to focus on the steps. So this is what happened for point 1. Okay, now for point 2. Okay, and we can, now this is the first step in this. So I can do it for first point, then second point, then third point. So this is step 1. So what we did is, we did that forward pass, the forward pass that we spoke about in the last lecture. We said that we have to perform this computation. So initially with this, now we have to apply sigmoid on this. So this is the aggregation function that we did. So aggregation, after aggregation, we will apply the sigmoid. So once we apply sigmoid, so what is, how to apply sigmoid? So you have to apply sigmoid y1 prediction is equal to sigmoid of 0.225. So what is the value of that? This is 1 divided by 1 plus e minus 0.225. So this is equal to, I think this is equal to some 0.566, 0.556, something of the sort. Okay, and values can be wrong, and you have to correct them. So what the first thing is, we applied the aggregation function. So this was our aggregation function. Okay, and this was our activation function. So we applied activation. The second and third step is that in this, so we had the step 1, then we had step 2. So I'll write 1 over here. So step 2. Step 3 is, now we have to calculate the loss. What is the loss because of this? How to compute loss? So loss is predicted y1 minus actual, and you have to square this, and then you will sum all for all the points. So this is 0.19. So when you take this value and when you take the actual value, so this is the loss, 0.197. So this is for point 1. So similarly for point 2, how to do it for point 2? So for point 2, you know that x2 is equal to 2.0 and y is equal to 0. Okay, and now you will do the same thing. You will have again compute the linear combination. You will compute z2, basically aggregate. So aggregation comes out to be wx2 plus b, and you know the values for w because we have said that you know values for x2, you know the value for bias. So this comes out to be minus 4.59. Similarly, this was step 1. This is our aggregation. So I can write it over here, aggregation. So after this, we'll perform activation. So how to perform activation? So activation function in this case is sigmoid of z2. So this is 1 divided by 1 plus e to the power minus 4.59. So this, if you compute, I suppose I'll look at the values. So this came out to be 0.010. So this activation over here. So when you apply this activation, so this is our predicted value. So this is y2 hat. So predicted y2. And now step 3 is calculation of loss. So loss calculation. So what is the calculation of loss? So you say y2 minus original y2. So you can square it up. So this comes out to be 0.0001, something of this sort, and you can again accordingly do for the third point. And once you do the computation, so then at the end you will compute mean square error. So initially here you are computing loss, so this is just square loss. And once you have to compute mean square error, let's suppose we also do it for point 3. So what we will do is, now we will compute loss for this particular weight for this particular bias. So what will that be? So you'll have to add them up and take the average. So 0.19 plus 0.001 for the third point, the loss came out to be 0.00036, and then you'll have to divide it by 3. So this is MSE. So this thing over here is mean squared error. So this is equal to 0.0657 roughly. Okay, this is what we did it by hand. Okay, so and then what we can do in the second step. So this, let's suppose we'll contain this. Okay, this is the weight, this is the loss corresponding to W, and the B that we set initially. What was the W that we set? W was minus 3.21. This was minus 3.21, and the bias corresponding to this was 1.83. And then we'll again say, we'll say that we have got this loss corresponding to this W and this B. Let's again randomly choose this W and B. Again compute the loss. Let's do it for 100,000 iterations, and we'll see the least loss. And corresponding to least loss, we'll have these weights and biases. We'll say that okay, this is the optimal weights and biases that we got in the 1000 iterations. So how many of you understood this? Let's now see the code and we'll write this code. So initially we'll define sigmoid the way it is defined. So we'll import, because we have to plot two things. We have to plot the curve fitting function, and we have to also plot the error surface, the error that we are getting. So I'll just import this code over here. So if you see, so these are the standard imports. NumPy and matplotlib. So this is not plain text, so this is Python. Okay, so now what I'll do is I'll define a sigmoid function. So you know how to define sigmoid function, so you can either use it from NumPy or you can define your own. So sigmoid of z basically is return 1 divided by 1 plus NP of exponent minus z. Okay, and then I'll compute this loss function. So this is the mean squared loss. So this is the mean squared error rather. Okay, you apply this sigmoid of x to the v. This is basically forward pass. What is happening over here? So you're giving this x value, you are giving the w, and you are giving this b, and you are applying sigmoid onto it, and then you are doing the mean of this. Okay, and then what we can do is we can generate 3 points in 1D. Okay, consider these 3 points. The 3 points that I showed you. These are the 3 points: 0.5, 2.0, 1.0, 10, and 1. These are the class labels. Okay, now what I can do is I can do say 1000 iterations. So consider this. So I'm saying n is equal to say 500. So I'll say 1000 iterations. Okay, so best loss is infinity. I'll start with infinity, and best W none so far, and best bias none so far, and we'll keep the history also. Okay, and we'll also keep the loss history. We'll keep the W history parameters of W, and these are the parameters, and we'll keep the loss history as well. So now what we have to do is I'll iterate through this for number of iterations. So if you see this, so I'm going for dashing this range and iterations. So I am randomly initializing W because we are doing random initialization. I am randomly initializing bias also. Okay, then I am computing loss. Okay, if you see, loss computation is happening over here, and this is using sigmoid. So I am doing the same steps that I told you, and then I am saying W history, append this W, and append this B, and also append the corresponding loss. So if the loss that I just computed, if it is less than best loss, because I have best loss here also, so if it is less than that, so you update the best loss, and accordingly update this best W and best B also. Okay, pretty standard code. And now after these 1000 iterations, I actually want to know the best weight and best bias. So I'll print those. So once this loop is over, so what I can do is, so I'll say that this is the best weight and best loss, and then I'll plot two figures. So the first figure that I want to plot is the sigmoid curve. Okay, I want to plot two curves. I want to show you those two curves. So this is plot scatter plot, and pretty easy. And then the second plot that I want to create, I want to plot is that's error surface. Let me plot this fully first, and then we'll plot the error surface. Okay, let me plot the error surface also. Okay, if you can see now, so I plotted the error surface over here, and this is the code that plotted error surface, and this is the code that plotted the data points and the sigmoid curves, and this is where actual thing is happening, and this thing. So this is by randomly taking these W's and biases, weights and biases, and then seeing what is the best loss, and I'm doing it for 500 iterations. So if I run this code, let's suppose, hopefully there is no error. So now you see this. So this thing over here that you see on your screen now, so this is the sigmoid curve, and you can see that a lot of other curves are also shown here. Okay, and these were the different other sigmoid curves. That was not the best fit, but if you see this black curve, this is the best fit. So here it passes through this point exactly, and there is some minor error over here, and there is also some minor error at the bottom. There is some error, but this is the least error that we have. And here the best weight was minus 4.14, best bias was 4.9, and the MSE, best MSE was this 0.013, and you know how to compute MSE based on given weights and bias. Now if you see corresponding to this error function, we have an error surface that we actually wanted to navigate. Okay, so we'll see that. So if you see this, so this was the error surface that we wanted to navigate. Okay, so if you see, this is we randomly initialized for all these red points by the random points that we checked. Okay, we checked this point, and we checked this point, we checked all of these points, we checked all around, and we got lucky in 1000 iterations, we got this. So this seems like the global, or I can also call it local, because we have just plotted it for some limited weights and limited biases. But you see this, so this over here, the z-axis that you see is giving the error. So x-axis over here, so if you see this is weight and this is bias like this, and then you see that this curve is a 2D curve if you see in that way. So this is the error. So you can see that the error is minimum over here. At the surface, error is minimum, and we got lucky in the 1000 iterations. We're able to get the best fit. Okay, if I decrease the number of iterations, by now what should happen naturally? We should not be getting the optimal value. Okay, let's check that. If we suppose do only maybe 6-10 iterations or something of that sort. So here, if I change this, so this was 500 iterations. If I change to 10 iterations, so you see, I think they still found it 10 iterations, and maybe let's consider 2 iterations. I don't know if it happens in 2 iterations. I just wanted to show you how to do more iterations. And now you see that this is not the best parameter. This is not the best fit. This curve is not the best fit. You can clearly see that it needs more iterations. And sometimes you will get lucky, sometimes you won't get lucky. So this is one of the ways you can find the weights and biases. But this is not optimal way to find the weights and biases, because you are just throwing arrow in the air and you are in the hope that it will land at the global or minimum, at least local optimal value, local minimum of this. So how many of you understood this? So what are we doing in this case? So we are taking these W's, taking these weights, taking these biases, giving random values, computing loss, and having this loss history. Where do we get the minimum loss? And then we are keeping it. We are not following any direction, and we are hoping here that we will get lucky somehow. So we'll find among these 1000 iterations, or in this case 2 iterations. So among, let's suppose, 10 iterations, if we got lucky, so what will be happening? So we'll get this local minimum value of this error. So we'll get this surface. Okay, in this case we got lucky, but it is not always the case. It will only take 10 iterations, and if data is more complex, we're only 3 points in this case. So we'll have more data points. We'll have thousands and millions of data points. Then this approach will not be good just by guessing the weights and biases. So it will have to do a lot of things. So now it boils. The question is now: is there an algorithm? Can we somehow find an algorithm which will guide us through? So any questions till here? Do you have any questions? Can I assume that you understood everything so far? The question we received that why are we using this sigmoid curve only? So in this case, as I said that on purpose, there were only these 3 points taken, because if we increase number of points, so you'll clearly see that we will fit some sigmoid, but that will not exactly fit. There will be a lot of error corresponding to that. So once the points are increased, let's suppose we have points over here, we have data points like this. So now we'll have bunch of sigmoids. So single sigmoid neuron won't be enough to model the problem exactly. So that's where we come up with a deep learning concept, because we'll have deep layers of these deep sigmoid neurons. So we'll have layer of neuron, and then we'll have second layer, third layer, or something of that sort. And then once we combine all of these, because I said what is deep learning? Basically deep learning is the composition of functions. So it is a very complex function which is composed of many functions. And if you only use sigmoid neuron, let's suppose if you use only sigmoid neurons, so what will you see is, you will see that it is composition of these sigmoid neurons. And I'll prove to you that by universal approximation theorem. So you can take these sigmoid neurons and you can approximate any function. So what I said is here, I don't want to find the exact solution. So my job is not to find exact solution. So I want to approximate. So what is the difference between approximation and exact things? So here I am now allowing randomness to take place. So if there is an exact solution, which in real world scenarios there is not, because you can have same features and there will be something different. So let's suppose you have these features xi to say, let's suppose xi1, so say xin, and this is equivalent. These all the features are same in some other j point, ji to x jn. So these are 2 different data points. So you know what? Sometimes they'll behave similarly. Okay, and that's what randomness gives us. So sometimes you have same features, but the labels you have, let's suppose if it is something you have to print output of that, it will be maybe same, it will be different. Okay, that's how randomness plays a part in these things. So we cannot say with surety that this will be like this, but there is a pattern. There is a, let's suppose this pattern, the pattern will be followed say 90% of the time. So you saw those distributions, so they are not all clear, that we don't have otherwise we can have closed form solutions. So what's the meaning of closed form solution? If something is deterministic, so if you know that after this will happen, after this will happen, after this will happen. So if you know a deterministic path, then you don't need machine learning per se. Why don't you need machine learning? Because the thing is, you can find this closed form solution. So by closed form I mean you can just plug in the value and you will get an answer. That is the difference between deep learning and programming. Okay, to just again tell you that, so in programming you have a deterministic solution. So in programming, let's suppose if you want to add numbers, if you want to do something, so you have a determinism in that. You know that if I have a, I have plus b, so this will be equal to some c, let's suppose, and you have a deterministic solution. But once you come into deep learning, say, so why do we need you in deep learning? So if I write this, so this is 1. So if I write this is also 1. So if I write this is also 1. So all of these are different. So how is your visual cortex able to tell that all of these things are ones? So that they're quite different. Okay, somehow there is some structure which is preserved. Okay, and this is because we have unpredictability here, we have uncertainty here, and that is what deep learning does. So in deep learning, we do not make deterministic rules like you have this, so this will be called 1. So somehow what we are up to is that we want to give some way, we want to have some way so that we can keep room for this unpredictability, uncertainty. So that's what we have in this. So what I was telling you people is that if you have this sigmoid neuron over here, so one sigmoid neuron won't be enough. Okay, and then by composition of functions, you want to get an approximate answer. You don't want to get an exact answer, because exact answer basically means there is a deterministic process, which is always not the case. Okay, and you don't leave anything to randomness. Okay, you don't leave any variable to randomness. As I said, that by random I mean that you will have data, and sometimes you'll have exact same thing, but they'll have exact different outputs. Okay, why? Because of randomness. So when I say approximate, approximation gives you that you now leave some room so that you handle this unpredictability. So deep learning, what it does is, it does not find the exact solution. It will approximate this. Okay, it will approximate the solution. Okay, I hope I got the point. And I prove to you that if you have this bunch of neurons, if you make this layer of sigmoid neurons and then another layer of sigmoid neurons, so you make this network deep network, so you can approximate any function. Okay, by approximate, I'm not saying you can find exact values of all things, but you can still approximate it to a good degree. By that good degree, you will probably have, let's suppose, error of 0.1% or something of that sort. Okay, and by approximating, you are saying that I am still leaving room for unpredictabilities. There will be unpredictability. And why are you leaving room for this? Because this is how real world is. The real world is not giving you the exact answer. So if you have all these parameters and if you know all these things, you still have to model it probabilistically, because some things will be here and there. So what probability gives you? Probability now gives you a model by which you can handle this, or you can at least frame this unpredictability and come up to the maybe a logical solution. So this is the logic. It'll also be wrong. So that's why we are approximating it. Okay, did I get my point through? Okay, now the question is that we are not well off with this random guessing. So this is not the optimal way to do the things. So now we should find some way, find a way. So what's the question? Basically, the goal is to find a way so that once we update these parameters, because we have to update these parameters somehow. So can we update these parameters somehow so that we can get to the actual solution? We should not take the random steps. The thing is, basically, it is like a drunken man. So if you see this error surface, so this error surface is, these surfaces were like hills. Okay, hills and valleys. So you had this something of this sort. So that you could imagine in 2D, 3D, you could imagine that. And you are having these, so they're called actually manifolds. So if you people, some of you might be taking topology maybe in future, so you will see that these things are called as manifolds. So you have to somehow navigate this manifold. Consider this. So we have this is our surface. So we have this hills and valleys. So you have to navigate these hills and valleys. So let's suppose this is your, say, global optimal, or this is your global minimum value. So what you want to reach this value. Suppose when you started randomly, so say you start at this point, or let's suppose you started with this point, suppose something of this sort, and you want to reach here. So if you keep on doing, updating these weights and biases randomly, so what will happen? You will maybe sometimes you will go here, 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 and maybe if you are lucky, and you will sometimes hit this, and you are keeping the track of the minimum value, and maybe you will get lucky and you will hit this. But we don't want to do this. So what we basically want is, we want to have a procedure, we want to have a mechanism by the help of which we should somehow get to this value in a good fashion. It should not be that we are doing it randomly. We should have some direction. Okay, so we want to move in a directed way. So we want to move on this terrain, on this surface, in some proper direction, Okay, so we don't want to move on the surface randomly. Sometimes we go here, then we jump, we go here. So what we can do is, so I'll tell you an idea how to do that, and then we'll try to mathematically model it. So now if you know the error surface, and you will know the error surface, because if you are given, you know the error function itself. So you know this error function. So you know the error function. So because of this error function, now because it takes values, this weights and biases, parameters basically called the theta, and then you have this x. So based on this x and this theta, so what this function will do is, it will give you the error, it will give you the loss that you have. Now you can construct the whole terrain, but you don't need to do that. And you can also visualize it in 1D, 2D, but you don't need to do that. So what you can do is, what if you can test it in the vicinity? Suppose you chose this point, okay, and then you don't want to find, let's suppose, global minima, you want to find local minima. Okay, the local minima, for example, for this point is here. So I'll make this diagram maybe a bit cleaner. So you have something of this sort. An error surface like this. So here I am constructing this error surface is in 1D, 2D, so I cannot go beyond this, but mathematics can handle everything. So let's suppose now what you do is, you selected this point randomly. So this was your initial guess. So now my idea is this: you don't need to navigate the surface. You don't have to again randomly do it, and you land up here. So can we somehow do this? So if you randomly initialize something, So can you now check the neighborhood? So if I can check the neighborhood, so if I check the neighborhood, that is in the vicinity of the point which I have selected, the random point that I selected. So it will maybe guide me. It can tell me either go up or go down, go up or go down. Okay, I'll see. So where should I go? I should basically go to this minima. So it is something of this sort. You have a drunkard person. The person he has drank till the throat. So now he wants to go to the valley. He wants to go to this valley. So once he drank alcohol, whatever he consumes, now he is high. So he slept and suddenly he got into his senses, but still he is so numb and he wants to reach to this valley. So now what he should do is, and maybe consider this, the guy cannot see anything now. The guy is almost blind. So he has to make judgments. So what a drunkard person will do is he'll start from a random point and then maybe check the vicinity. Is it going down or is it going up? If the person feels that, oh, so if I take step in this direction, I'm going up. If I take step in this direction, I'm going down. So he'll slowly take this step and again check on this step. Oh, is it good? So you might have seen it with yourself also. So in the night sometimes when there is no light, there is only darkness. So if you want to go to certain places, you check your vicinity. You keep on checking your vicinity. Okay, am I going in the right direction? Am I going in the right direction? So that is the principle we want to use there. So whatever point I am choosing, I want to check the neighborhood and I want to see, based on the neighborhood, I want to decide on the direction I want to go. How many of you understood the crux of the concept? So the question asked was, so we can get stuck in these local minimas. So that is very true. So once you use this gradient descent, because gradient descent, the crux of the concept is that you are choosing a point randomly and checking your vicinity, checking your neighborhood. So which direction should I go now to find this local minima, to find the local optimal point, and it will not give you the global optimal. It will always give the local optimal point. And sometimes you can get stuck in here. So you can get stuck in here because you have no direction. It is like you are blind and you just have some senses working. You can just check it. It is not that you can just see the function. You can zoom on this function and you can check. Okay, and you can pinpoint. Okay, this is the minimum. You can do it in one shot. Okay, you cannot do it in one shot because these terrains or these manifolds, the arrow surfaces which I call, these are very complex. So this arrow surface is just in 1D. The arrow surface can be in, let's suppose, it depends on how many parameters you have. So these many dimensional parameters, these many dimensional manifolds are there, and then you have to check. Okay, where to go now? Okay, this is the goal. So the goal is to somehow navigate this arrow surface in such a way so that we take steps in the right direction at least. Okay, and we should not take a lot of steps also. So what might happen? Let's suppose you found this and you say, okay, this is the direction. If you go all the way, let's suppose you went to here. Let's suppose you went here, and at this point you again took a bigger step. Say you went to this point now. After taking the step and you went to this optimal. So you can also keep on fluctuating. So that's why you have seen that in the gradient descent we take smaller steps. Okay, the point there is you don't have to take a larger step because you can keep on fluctuating. You can go from this to this directly. If the direction, let's suppose, is telling you have to go in this direction. If you took a longer step, so you'll reach here, you will not reach on the surface. Okay, and this will not be a good step. So now you also understand the rationale behind taking small steps. Okay, and because of these things, now how to adjust these steps? This is called learning rate. We have a separate class on learning rate. So because of this learning rate, you have different types of optimizers. Okay, and they adjust these learning rates. Okay, now a lot of these training depends on learning rate. So initially learning rate should be high, then you should decrease slowly, and then you know about Adam optimizer. A lot of optimizers are there. So basically, many of these they adjust these learning rates. So how they adjust these learning rates? There's a mathematics behind that. You should not take a large step. Okay, and you should not take small step that much. Okay, and there are a lot of things that have been done in this learning rate because we should not keep on toggling here. We should not keep on going from here to here. So we should take reasonable steps so that we reach this local minima. And I understand there is a problem that you won't be able to reach global minima. But this is not always the case. So you won't be able to reach by using gradient descent. And second problem is with the learning rate. So what is basically learning rate? Learning rate basically is what is the step. So how much are you jumping? So that is called learning rate. We'll also see all of these terms in depth, but here I just want you to know the term. So here once you take this step, so actually we want to find the direction. Okay, now let's have a mathematical treatment of direction. So what do we want to do? Okay, so initially once we have this parameter, so you have this theta. Theta is this weights and biases. So you have this is a set of parameters. Now what you basically want, the objective is to find the parameters. The objective is to find such parameters, such W and such theta, such W and such bias so that we get the minimal loss. And now we cannot do it in one shot. So we have to do it iteratively. So we have to do it iteratively. So how should the iteration work now? So at each iteration we'll have to somehow update these. So we'll have to change this w. So we should be change of theta. So how much should the objective is to find this update now. So update is how much to change this w and how much changes this b. So this is the goal. And goal is to find such theta, and now this theta new. So this theta new basically is this theta plus learning rate, okay, multiplied by delta theta, delta of theta. So you have to find such delta theta, so that if you compute the loss, so you will have loss function is dependent on loss of new, and you have loss of initial loss. So loss new should be less than loss of this theta. So initial, the new loss, the final loss should be less than. So this is the goal. So mathematically what I wrote is, so I should do this. So initially I started with this. This is my initial weight and bias. So I have this initial weight, I have initial bias. So I have to change somehow. I have to do this. I have to do updation. This is my update step. The, delta w, delta b is the updated. So what I have to do is I'll have to change this delta theta. So how I'm changing? I'm adding this thing. I'm adding this thing, this delta theta. So whenever I find this, I have to find this. This is basically I have to find this. So that I have to find this in such a way so that if I add these things, if I add this w, delta w and delta b to the initial theta, so I'll get this delta nu. So this delta nu will have a corresponding loss at steady phase. So this loss should be less than loss of theta. So how many of you understood this? So this is my objective over here. So if I show you this, basically what I am here, मान लेते हैं, let's assume that this is our theta initially. This is why we started. And now what I want is, I basically want my w theta to be like this. I want my updates in such a way so that, let's suppose I go to this. So this is my delta theta. Okay, now I have, this is, once I compute this is my delta theta and this is my theta. And now once I add these things, I'll get over here, I'll get in this direction. Okay, and this is what I want. And now I will not take all the steps, I'll not take all of this. So I'll take maybe baby steps. I'll take n of delta theta. Okay, this is my theta new. Okay, and this is once I apply the algorithm. So this is my theta initial parameters, and this is my change. So once I change it, so I have to go to this, but I am not taking all the way. I'm not saying it. I'll go all the way to this. So what I'll do is I'll only take this much step. Okay, I'll only take this eta of delta. Learning rate will be very less. So this learning rate usually is less than 1, greater than 0 and less than 1. So we keep it in very small steps. Okay, this is what we want. So I hope, and why do we want this? So when we add these things, so we have to somehow deal with theta. So again the same question arises. So we have done this question again. So now what should we do? Somehow we should decrease this angle. So now we should somehow do such a way so that once we have this, so this loss, the loss we have over here and the loss we have here, they should have this relationship. And now we'll again go to our cos beta, because we'll perform a dot product and we'll see that angle should be between this and that, and we'll do the detailed treatment. Actually, how to do this now? So before doing the treatment, now the question is how to do this. The question is how. So I told you two things. I told you that this is what we have to do. We have to somehow find this delta theta so that we take the right steps. Now how to do that? The crux was that you have to see the error surface and then you have to see the neighborhood. Okay, in the error surface, you have to see the neighborhood. So once you see this neighborhood, and then you will take a guess based on that. And now how to find the neighborhood of a function? You again have to approximate. You have to use something to approximate the neighborhood of a function, and that will land us to Taylor's series. The question lies in Taylor's series. So what I'm telling you that my job here is I have to see how is the function looking in the neighborhood, and how I can approximate an error function in the neighborhood. So I can approximate any function by Taylor's series, or we can call it Taylor's approximation. So I hope that you people know a bit about Taylor approximation. We'll talk about it in detail maybe. So I'll just tell you what Taylor's approximation is, and maybe we'll then cover the gradient descent algorithm in the next section. So now what is Taylor's series? Now I know that the thing that I have to do is I know the error surface, and at a certain point I have to get to some neighborhood in the vicinity of that point so that I know what step to take. Okay, now I will use this Taylor series. So what is basically Taylor series? This concept basically is telling you that you can use polynomial functions to approximate. You can use polynomial functions to approximate any complex function. If you have a complex function, okay, what you can do is you can take a polynomial function and you can take a combination of polynomial functions to approximate it. So what are the polynomial functions? You can take a linear combination of these. So let's suppose you can take c0 x0 plus c1 x1 plus c2 x cube plus c3 x to the power 4, and once you combine them, so you have to linearly combine them. You take a linear combination of these of n degree polynomials. By n degree I mean you can start from 0, 1, 2, 3, and then you can approximate any function with this. This can approximate any function. So how many of you have seen this in calculus? Okay, so here I'll just define the Taylor approximation. So what is Taylor approximation then? If you have any complex function, it can be sine of x, it can be a composition of a lot of functions. So Taylor approximation says that you can take a linear combination. You can take linear combination of n degree polynomials. N degree polynomials, and you can approximate it. And the more terms you include, and you will have a better approximation. And this approximation is rather at a certain point. So it is a point, it approximates near to one point. And once you do it to n degree, because once you do it to infinity, that's why it's called series. Okay, and this series can even converge or diverge. So this can converge or diverge. So it is not a short thing that for a point you will write Taylor series and then it will approximate that. So if that approximation converts, you probably will have a solution. If it diverges, let's suppose in case of log it diverges, so you will not have, let's suppose at certain points you will not have this Taylor series approximating that exact thing. So what I want you to remember is that Taylor series is a way it takes linear combination of these n degree polynomials. It starts from, let's suppose, x to the power 0, x1, x to the power cube, x4, something of this sort, and it takes a linear combination of those to approximate any function that you have. And here error function is a function. Okay, the error function, the terrain that you have, okay, the error surface that you have, it is defined by a function. At that function, what we can do is we can approximate any of these error functions by using this Taylor series. And once we do that, so the basic thing is we're up to this. We want to find this. We want to basically find how to update this. So this is what we want to find. We want to find this delta theta. Okay, so what is the direction that I should move in? Okay, and then this eta will tell me the learning step. That now the topics we will study is Taylor series, and then we'll see how gradient descent, how gradient descent is derived from Taylor series. And then we'll apply this. We'll apply gradient descent. On the problem that we earlier did. So we'll apply the gradient descent algorithm on the problem that we did today. So that the problem that we had 3 points and we're applying sigmoid on that. Okay. So we'll have to learn that. We'll not now guess. So what we'll do, we'll try to find these weights and biases by using gradient descent. And in that process, we also have to compute gradients. And how to compute gradients, we'll do that by backpropagation. Okay, and this will be the plan. And once we understand this theoretically, so once we understand this, and we'll code all of these things. Okay, and then we'll start our coding things. So we'll code it, and the code won't be optimized. That code will be probably terrible, but it will be just to showcase you. And then that code has to be optimized. Okay, and by taking this the code and you optimize, then you can create a library out of that. And each of you people, why am I telling you this? So I'm teaching you theory right now, and then we'll go to code, and you will have to optimize that. And once you have that, each of you will at least implement 1 or 2 algorithms. All of you will implement backpropagation on your own. Okay, so all of you will implement backpropagation, and people among you, some people will implement a different version of gradient descent, SGD, and there are a lot of types of optimizers. So you will implement all of these, and you will also have to implement a lot of activation functions. So to call it a library, we should at least have a lot of these functionalities. We should have a lot of activation functions. We should have a lot of optimizers. We will have optimized backpropagation, and what else can we do in that will come in the engineering problem. The first you will have to bring the thing into existence, and then you will have to optimize it. Then second phase is the engineering problem that you will solve. And by the end of deep learning, so what you at least should do, you should have a library that this class has built. This class should have built backpropagation from scratch. They should have built gradient descent. They should have built all of these concepts from scratch. And if time permitted, whatever architectures we learn here. So if you learn about a transform architecture, if we learn about, let's suppose, convolution neural network. So all of architectures also should be implemented in this library. So this is the goal of deep learning. The goal I'm setting you here is to come up with the library which can be used by any person to learn. If not, it cannot replace PyTorch, because PyTorch people have a lot of resource and they have a lot of people working for that, and they have very smart people and very high experienced people who are working for PyTorch. But in this group, I want you people to make a library so that this can be used for learning. People can learn from this. So you can write step-by-step documentation. How did we implement this algorithm? And maybe after a while you will see that people making tutorials on those. People making tutorials how to code backpropagation, and this will be a separate course on ML systems rather. I won't teach you ML systems. Because people here, if you are for computer science, if you want to code on your own, you will have to do these things. And maybe I'll help you, we'll together do it, and you will have to have a presentation on these ML systems. Because the first thing is to just write a code, to bring it into existence. And the second thing is to make it optimized, to use the ingenuity of engineering and to use state-of-the-art methods. So how and exploit the architecture, and then see how can we exploit the current architecture that we have in computers to perform the optimized operation, so that these things seem fast. Okay. And what I want you is now goal for you people is to make a library that people should use for learning deep learning. Okay. Because I believe that deep learning, the way it is taught right now, people usually are teaching it just writing some theory, import statement, PyTorch, and this and that. That is not the way to learn deep learning. That is just the consumer minds to your consuming stuff. So rather than come up with these big concepts, come up with these concepts on your own. And the second thing is, we are just trying this with sigmoid neurons. We are trying this with, let's suppose, with the neurons that started from perceptron. And there are other ways of approximating functions as well. Okay, there are Fourier transforms. There are other at least 4 or 5 ways which I know of by which you can approximate these functions. Because the goal in deep learning is to approximate functions. So you are given some input and you are given some parameters. You have to approximate function. You have to come up with some function which will approximate other function. And there are a lot of methods that can be used to approximate the functions. What I want you people to do is that you should find these methods and try to code them up. Try to code and try to first understand the theory behind them. So once you understand the theory, and then you have to bring that thing into the code. And that will make you a better thinker, and that will in turn make you a better engineer, better software engineer, or that will rather make you a better scientist if you can think on those lines. If you think, okay, I'll implement Fourier transform on my own. I'll just read its theory because I know I went through a process. I saw what neurons are, and then I implemented them, and then I implement backpropagation. Now I have a library. Can I do something of this sort? So this is where you will at least jump the levels in that consumer ladder, which I was telling you that there is a ladder in that we are maybe in the middle of consumer, so you want to jump that ladder. That is the goal, and you will learn from a rediscovery point of view. It will be something that you have discovered for yourself. You just read the theory, and sometimes some concept will hit you, and it will be like, oh, can I train the network like this? So if you will be able to train network like this, because still I believe that backpropagation is not the optimal way to train networks. Okay, you should come up with some different methods to train the networks. But if you are at the point where you just import PyTorch, dot backward, dot optimizer, dot grid, then there is no chance of doing these things. But if you do it from scratch, I hope that some of you will hit an idea, and if we have enough discussions, these people will come with better ideas than other people. And maybe if you code it up, it will give good results, and it can be a great contribution.